Okay, in this tutorial we'll look at Taylor series. So Taylor series are a special type of power series of the form Tnx, like this, f of a plus f prime of a over 1 factorial, then x minus a plus f double prime of a over 2 factorial. Then we have x minus a squared plus, this continues to go up to saying f of the nth derivative, then a of n factorial, then x minus a to the power n. So this is a general form of how a Taylor polynomial series looks like. Alright, so given a function, you have a function f of x. Consider this function, and it's c1 c0 c1 x minus a plus c2, that's x minus a squared plus, okay, going like that. Then we're saying by putting, so if we substitute, so we say x equal to a. So where there's x, if we replace a, we will have that f of x is going to be c0 plus c1. Where there's x replace a, we have a minus a. Then here we have c2, we have a minus a squared plus all the way like that. So then this here becomes 0, and there becomes 0, and all other terms that will be following here will become zeros, and they'll multiply, and I'll just remain with this constant here. So f of x is just going to be, so f of a, because we've replaced a, is going to just be c, is just going to be c0. So I'll just remain with this here. What if I differentiate the function now? So if I differentiate the first integral of the first derivative, I mean, of the function, f of x is going to be, so of course this is a constant, differentiate a constant, you remain with 0. Then you have c1, then here it's to the power 1, so 1 minus 1, we get 0 in the power, and this becomes 1, so I just remain with c1 plus, there I have 2 in the power, so 2 multiplied by this here, I'll get 2c2. Then I subtract 1 from the power, I'll get x minus a, like that. Then it will remain like this. Then for the term that follows, that will be 3 c to the power c3, then x minus a to the power 2, like that, and it continues to go like that. So now if I substitute in this here, I substitute a equal to x, so meaning this here where there's a minus x, this here then becomes 0, that 0, and every other term that follows will become in that way, meaning f prime of a is just going to give me c1. Okay, so I can continue this, for the next one. We're saying, if let's say I find the derivative, the second derivative now of f of x is going to be, so it is going to be 2c2. Then instead of me writing this one here, as I can observe, this power here, when I differentiate, this 2 multiplies with the 2 there, so I can just write it as 3 multiplied by 2. Of course it's 6, but we write it in this way because it will be useful as we go on. c3 x minus a, like that, plus, then I have the next one, meaning the next one will be 3 multiplied by 4, like that, c4 x minus a to the power 2. So this continues to go like that. Then at f of a, f double prime of a, when I replace a, I just have, so these, everything that has an x term there, when I replace a, they become zeros, and I just remain with a constant, which is 2c, like that. And this can continue in this manner of just doing the same, where I find now the third order derivative, then it will still give me the same form which we are getting. So now if it was the third order like that. Then I replace a. When I replace a, I'll just remain with a part which has the constant, and that part is just going to be 2 by what 3, which is 6. But yeah, 2 by 3 like that. And I can write this 2 by 3. Okay, if you see it, maybe let me write it as 3 by 2. So 3 by 2 like this, C3. So I can write this part here as 3 factorial, because 3 factorial is just 3 multiplied by 2 multiplied by 1, which is the same as 3 by 2. It's just going to be like this. So now this here and my C what? My C3. So in a more general form, this means if I have f to the nth derivative, I don't know to what the power of derivative, and it can be, so we're saying when we replace a in the function, this is just going to be equal to n factorial then cn. So it's going to give me this in this general form, where cn is just the constant or the coefficient of the series. So now cn, if I was to divide here n factorial on both sides, I'll remain, and I have cn is going to be fn a like that divided by n factorial. So this is what I'm going to get. This is what I'm going to get that the coefficient is. So now the theorem is here. Theorem is, if we have a power series, that is the power series at a, let's say at a point a, we're saying the power series at a point a, and the power series is given, let's say f of x is equal to summation of that from n 0 to infinity cn x minus a to the power n. If we have a power series, in this case the general form, then the coefficients of this power series is given by the formula which we just from deriving, that would be cn fn like that a then divided by n factorial. This is how it's going to be. Then if it's going to be like this, it means that the Taylor series in general is going to be f of x to be equal to summation. Okay, so if you can see in this in this power series here, where the cn here, we can replace what we found, and we will have that like that from there. Then f nth derivative a over n factorial is just going to be x minus a to the power n. So I get that when I replace this cn. So at the point we're saying it's at a point a. So at a point a, when I replace a, I'll just be getting f of a plus f prime of a like that over 1 factorial. Then this is x minus a plus, so that will be f double prime of a then x minus a squared over 2 factorial plus, and this continues to go up to what? Up to infinity. So this is the general form, as we are saying, of the Taylor series. So now at the point, as we said, at the point where we have what? We have a, then this general form, or just from writing, that will be the what? The Taylor series. But then if we were to replace our point at a, we're saying we replace it, becomes a equal to 0, then this Taylor series becomes in the form, we're saying f of x summation of, so from n to 0 like that, f n, then we're saying we replace 0 where a is, n factorial, then x n like that. So we are seeing that where we had x minus a, here when we put 0, x minus 0 will just remain with x, and to the power n, and that n will just distribute like that, which is this xn there, which I am getting in this part. So when I replace 0, I get this. And of course, when you expand this, you just be getting, this will be f of 0 plus f prime of 0, x over 1 factorial plus f double prime of 0, that will be x factor x squared over 2 factorial plus f triple prime of 0, then x cubed over 3 factorial plus, then it continues to go like this. And where a, when we replace a equal to 0, this is also a special type of Taylor series which we call the Maclaurin series. So this is called the Maclaurin series when we replace a equal to what? To 0. Alright, let's now look at an example of a Taylor series. So we have this question here, and it says, let f of x equal to the root of x plus 1. They're telling us compute nt of x at a equal to 3 for n equal to 0, 1, 2, 3, 4. So in this case, they have not said we should generalize like n, but they've given us exact points of n to use. We are using up to 4. Then that's what we have there. So how do we work out this question? So our solution is going to be, so we have f of x first of all. So here let us get the derivatives. So we'll get the derivatives from 0 up to what? Up to 4, and we'll be working with that. So we have f of x. Of course, f of x, we have its root of x plus 1. It's already given in the question, but this can be written as x plus 1 like that to the power 1 over 2. Then f prime, so f prime of x. Okay, so when I drop my power there, I'll have 1 over 2. Then x, so x plus 1, then I subtract minus 1 in the power, I get minus 2. Of course, here finding the derivative of what's inside, when I derive versus find the derivative of x, it's just going to be 1. The derivative of a constant is just 0. So 1 multiplied by this, I still get the same thing here which I have found. And that will be the case for each and every one of them because there's x plus 1 inside there. So then I have f double prime of x is going to be equal to, there I can drop the power and multiply, so negative half multiplied by half, and I get negative 1 over 4. Then this is x plus 1 like that, negative 3 over 2 the power. Then I can go f triple prime like that of x is going to be, I multiply this 3 over 2 multiplied by 1 over 2, that's going to give me a positive because negative by negative, and I get 3 over 8 to be equal to x plus 1 minus 5 over 2. Okay, then I have f to the, so when I reach 4, writing 4 like this, f 1 2 3 4, you have a lot of them coming, and that is going to be so laxsome. So just then start writing the numbers. So you just write 4 like that, then of x, and this is going to be equal to negative 15 over 16 x plus 1 to the power negative 7 over 2 when I subtract minus 1 there. So this is what I get. These are the first 4 derivatives that I'm going to use. So now I must evaluate at a point where x is equal to, where a is equal to 3, where a is equal to 3. So if a is equal to what? To 3, we're saying, okay, so this at a equal to what? To 3. So f of 3. So in the function f of 3, we must replace 3. So we have x, the function is x plus 1. So where there's where our a, we replace it where x is. So that will be 3 plus 1 like this. And then this just gives us root of 4, which just gives us 2. Then I do the same for the others. So I have f prime of 3. When I replace that, I just get this will be 1 over 2 root 4, and this is just going to give me 1 over 4. Then I go on to the second one like that. Then this is going to be negative 1 over 4, then root of 4 like that to the power 3, and this here gives me negative 1 over 4 to the power 2 like that to the power 3. and this is going to be negative 1 over 32. Then I continue, f triple prime at 3, it's going to be 3 over 8, I replace there root of 4, then 5, and this is going to be 3, that is 8, 2 to the power 5, and this just gives me 3 over 256. Then I do the same for the fourth one, which is the power 4, 3 like that, and that will be negative 15 divided by 16 root over 4, then this is to the power 7, and this is negative 15 over 16, then 2 to the power 7, and this is going to be equal to negative 15 over 248. So I get these values here after I do that. Now I'll keep these values, they'll be of very great use going forth. Then I must then find the coefficients. So must then find the coefficients. So as I said, the coefficients are given by Fn, like this, a over n1. So now to get this coefficient, so for the first term, we're saying for the first term, it's a constant. The first term is always a constant, and if it's a constant, our term will just be f of 3 is equal to 2. Then the second one, so the second term is the one involving x minus, at this point our a is what is 3, so it will be x minus 3, and this is going to be, it's the one which is given by f prime of 3 over what, so we said it's n factorial, so it will be 1 factorial because the power there is 1, so that will be 1 factorial. Then this becomes what? So I already found this f prime of 3. As you can see in this previous page, it's 1 over 4. So I replace the 1 over 4, then 1 over 4 divided by 1 factorial, which is just 1. I'll remain with 1 over 4. Then I check the next one, which is 4x minus 3 to the power 2. Then that will be f double prime of 3, then down there that is 2 what? 2 factorial. Then that is going to be, so I found this f double prime at 3, which is just this here negative 1 over 32. So negative 1 over 32 divided by what? 2. So divided by 2, that's the same as saying multiplying by 1 over 2, which is a half, and this is going to be negative 1 over 64. So I get that value there. Then I continue, I go for x minus 3, and I have f triple prime of 3 over 3 factorial, and this is just going to be that value which I found, which was 3 over 256, like this, and that will be 3 factorial is just 6 because it's 3 multiplied by 2 multiplied by 1, this is 6, so I get this is dividing by 6, which is same as multiplying by 1 over 6, and this is going to be 1 over 512. Then I do the same for the fourth one, write it here on top, that will be f the fourth, like that. So this is the term involving x minus 3 to the power 4. So it's going to be like that. Okay, let me just erase this part. Okay, the term involving that, which is going to be equal to that to the fourth over 4 as this factorial. Of course, this was evaluated at a equal to what, to 3, and this will be negative 15 over 2048. So 4 factorial is just 24, so that's the same as saying 1 over 24. And when I work out this, I just get negative 5 over 16,384. So this is what I get. Now after getting this, I can write now the first 4 terms of the polynomial. So the first 4 terms, okay, let me start with the one, let's say at 0, because they told us at 0, at n equal to 0 of x, like that. Of course, when we evaluated that constant, we are just getting that that is 2. So I replace there, that is just going to be 2. Then for the one at 1, we are saying, of course, meaning you have this point up, so it's going and expanding just up to 1. So you have the one at 0, which will be there 2. Then you say the one which was involving 1, and of course we found the coefficient. So the coefficient which we found was 1 over 3. So we found 1 over 3, 1 over 4 I mean. Then there we are saying it's x minus our point A is 3. Of course the power is 1. So what we are doing here, we're just getting f of n divided by n factorial. Then at the point we have a, then x minus a to the power what? N. So at those points, that's what we're now getting here. So since this was for 1 and 1, it ended there, so we just end there. Then we get 2 here of x, and this is going to be 2 plus 1 over 4 x minus 3. Then for the other one, I still get the coefficient that I found, which was, as you can see here, I found this one, which is negative 1 over 64. So I have 1 over 64. Then 1 over 64, that is x minus, so the point is 3 to the power n is what? Is 2, because we're adding up to 2. Then the third one, meaning is this one, we have 2 plus 1 over 4 x minus 3 minus 1 over 64, then x minus 3 to the power 2. Then the coefficient of that one was 1 over 5, 12, like that. Then that is x minus 3 to the power 3. Okay, then the fourth one, which is the last one, which they're asking for, that will be 2 plus 1 over 4 x minus 3 minus 1 over 64 x minus 3 squared plus 1 over 51 over 2 over 512, then x minus 3 to the power 3. Then the one that followed had a coefficient of 5 over 16,384, and that is for the coefficient x. So that is this part, which is x minus 3 to the power 4, because it's for the fourth one. So this is the fourth versus Taylor polynomial series. So this is how we work out Taylor polynomial series and the basics of it. Alright, if you're new to this channel, remember to subscribe and like this video.